us. So we'll say some things. So while things like particulate radiation and mechanical waves are types of kinetic energy, um, kinetic energy is the energy of motion. Um, Kinetic energy happens when massive objects move. What I mean by massive is I don't mean like a cruise ship. I don't mean a big thing. I mean a thing that has mass. Okay. What we'll learn later in now-ish and in the upcoming days, we're going to talk about electromagnetic radiation. And one of the facts about electromagnetic radiation that we didn't say when we talked about Röntgen is electromagnetic radiation, light waves, are massless. They don't have mass. They aren't made of like a thing that you can hold. Okay, but particulate radiation is. They're little pieces of matter. Fire. You saw it in the cloud chamber. Little pieces of matter being shot away from the unstable atom. Mechanical waves are little pieces of matter all moving collectively, right? When I talk, I'm compressing atoms in the air the gas in this room, and those compression waves are traveling towards you. Those are forms of kinetic energy. In order to have kinetic energy, you have to have mass. Now, what's great about energy, this is another thing that we'll talk about in more depth, is that energy is conserved, but it can change forms. So what I mean by that is kinetic energy can be converted into other types of energy. Okay, for example, when I slam my hand down on this desk, right? I took my hand and I moved it real fast towards the desk, right? I gave my hand kinetic energy, okay, energy of movement. When I hit this desk, I converted that kinetic energy into what? Well, kinetic energy of other things, of the air in this room. That's why you guys all heard it and jumped, right? I'm converting energy into other forms. I also heated up the desk a little bit. If I had a nice, really, accurate infrared thermometer, and I measured the heat on this desk, and I slapped the desk, and I measured it again, that desk will be just the tiniest bit hotter after I slap it. Okay. So energy changes forms. Particulate radiation that this meter's detecting is a form of kinetic energy, little pieces moving fast. Mechanical waves, like sound and water waves, are little pieces moving through space. Yeah?
Okay, so particulate has mass.
Yes.
But sound waves have no mass, but they are waves.
The sound wave, though, is it's radiation because it's energy moving from me to you, right? But what is moving are the air particles. I'm giving the air particles movement, right?
They're not a part of the original thing. They're just the air particles between here and there.
They are the wave.
They are the wave.
The air particles are the wave. They're made of the wave. Rather, say another way, the wave is made of those air particles. If I don't have those air particles between you and me, we have no sound traveling between you and me, right? There's no wave traveling between you. So say it correctly. The wave is made of the particles in the air in the room, right? The wave is made from those particles. But importantly, electromagnetic waves is radiation, but it's radiation energy moving from one place to another without moving any physical object. Okay? The energy from the sun travels from the sun to the earth without moving anything between here and the sun. Okay? They travel through the vacuum of space, right? That's why I can see, the stars in the night sky, because the stars shine their light. That light travels through space, empty space, right? And gets to us. Normally, when we think about radiation, right, like sound, for example, there has to be something between me and you in order for that radiation to get to you. In order for the energy to get to your ear and vibrate your eardrum, there's got to be molecules in the air that I'm moving around. Okay? Electromagnetic radiation transfers energy without moving anything. Okay? So electromagnetic radiation are not a form of kinetic energy. They're a form of what's called potential energy. And we'll talk more about potential energy later, but they're a form of potential energy. And I'm just going to say it now, and in later lectures I'll defend it, but electromagnetic waves are a fluctuation, a wave, in the electric and magnetic field. There is a double wave. The electric field waves one way, and the magnetic field waves perpendicular to that. Again, I'll defend that later. Right now, we'll just say that that's true. So that's what a light wave is. It's a wave in the electric and magnetic field. When it hits your eye, if it's the right kind of wave, you can see things. When it hits your skin, if it's the right kind of wave, you feel heat. Okay? If it's the right kind of wave, like an X-ray, it'll just pass right through your body, okay, and hit an image receptor behind your body. Importantly, right now, they're massless. It's not a thing moving through space. It is a wave in the electric and magnetic field. So there is something between you and me. It's the electric and magnetic field. Okay, when light comes from the ceiling and gets to us, it's traveling through effectively. I mean, it would do it if the room were a vacuum, if there were no air in this room. So it effectively can travel through empty space. But there is something between you and me. It's the electric and magnetic field. Okay, the electric and magnetic field, like other fields, pervades the entire universe. It's everywhere. It doesn't have a value everywhere. It's not that there is a wave everywhere in the universe. It's that the field is everywhere, and a wave in that field is a light ray, a photon, a piece of light, a quanta of light, if you like, from Planck. Okay, so that's what the waves are. Is there a wave in the electric and magnetic field? They need no medium. They don't need to travel through matter, and they are not matter. Now, some types of radiation, particulate radiation and X-rays and things like gamma rays, are high enough in their energy. We'll talk more about energy later, but they have high enough amounts of energy to where if these particles or waves happen to run into an atom, they can break apart the atom. They can take and break pieces of the atom off. Okay, we call it when an atom is broken apart, we call it ionizing the atom. Okay, so atoms in nature, nature would love it if all of the atoms were neutral. Nature does not want things to have charges, right? You ever left a battery in a drawer for a couple of years and then tried to use the battery, right? Dead, right? It was charged, it is now not, because nature just let it run out, okay? Nature would be really happy if everything was not charged, all right? So atoms like to be neutral. Atoms like to have no charge, okay? So a happy atom is an atom that has the same number of particles in the center, in the nucleus, as it has, so the same number of positively charged particles in the nucleus as it has negatively charged particles orbiting around it. Said in another way, atoms are happy when they have the same number of protons in the nucleus and electrons orbiting. Okay? For example, the hydrogen, if you look up at the top left of the periodic table, there's a big H in that top left box. Okay, that's hydrogen. Hydrogen's the most abundant element in the universe. Most of the universe is made of hydrogen, okay? Because most of the universe's mass is from suns. Suns burn hydrogen. Hydrogen has one proton in its nucleus. It only has one thing in its nucleus, okay? It's a proton with one positive charge. Orbiting around the nucleus of hydrogen is one single electron, one single negatively charged electron. Those charges balance out. The atom of hydrogen is happy to an extent, but for right now I'll say it's happy if it has one proton in the center, one electron orbiting. It's a happy atom. Same thing with helium. Helium has two protons in its center and two electrons orbiting around it. It's happy, okay? Neutral. When an atom is struck by a particle of radiation, either alpha, beta, or a wave of electromagnetism like gamma or X-ray, those types of radiation have enough energy to where if they hit it, as it's shown here, they can kick out an electron. You can't kick out the protons, okay? But you can kick out electrons from atoms. Okay? When you do that, you've removed one of the negatively charged things from an atom, so this atom now has an overall positive charge. You've removed one of its negative charges. It was neutral, so it's now positively charged. This is called ionizing. It's one of the main important terms you're going to have to understand in radiography. This is why X-rays and other forms of radiation are harmful, because ionizing an atom changes the way the atom will interact with other atoms around it. And remember, everything's made of atoms, and chemistry says that atoms join up and break apart when their charges change. Okay, when the structure of the electrons on an atom change, atoms will break apart from other atoms or join up with other atoms, forming molecules, right, or breaking molecules. Okay, your DNA is one of those molecules. Yeah, so ionization leads to chemical changes in atoms, which can result in harmful biological changes. Said in another way, ionizing radiation can hurt living things. So this is why radiation can be harmful. This is why visible light is not harmful to you. Visible light is low enough in energy to where it doesn't do anything to you. It gets to you and sort of bounces off of you and then radiates to other people in the room, right? But it's low in energy. X-rays, gamma rays, alpha and beta particles, which later on in another lecture I will identify the energy that these have and how that relates to like the energy of things like visible light. But right now I'm just saying they're higher energy than things like visible light. So these high energy types of radiation can ionize atoms, and we're made of atoms, and our atoms like to be in the shape that they are, and our molecules like to be in the shape that they are. And if we change that, we change the structure, we change the building blocks of us, and that isn't necessarily a good thing. Okay. Now, to be clear, your body and your DNA is always randomly mutating. That's where cancers come from. That's where that's where all of evolution has come from, is the random mutation of our genes. But radiation can increase the rate that this happens at. Okay, we don't want to necessarily increase the rate of mutations happening in our DNA, but radiation can do that. Okay, that's why radiation's not a great thing.
So
Yeah.
can you like irradiate water and then get people sick from that water?
So yes and no. Okay, so if I take this bottle and I go into the X-ray room and I just X-ray this bottle, right? I've irradiated the water, but after I turn the X-ray machine off, the water is not radioactive. Okay.
So wouldn't that be changing the molecules of the H2O?
Yeah, I can turn some of it into hydrogen peroxide, small amounts of it into hydrogen peroxide. So yes, I can turn it into hydrogen peroxide, but no, if I do that, I won't be giving you radioactive water. I'll be giving you some water with a little bit of those molecules converted into H2O2, but the water's not radioactive. Now, if I go to some fresh water supply for some country and I detonate a nuclear bomb, okay, and irradiate their water with particulate radiation, then yes, I've made the water radioactive, okay? And now that radioactive water is going to circulate to all the people, they're all going to drink it, and they're going to get that radiation inside of their body. So particulate radiation and electromagnetic radiation, totally different things, but they both can cause harm like this to the body, this type of harm. Hopefully that answers the question. Okay. About 1/2 of all the radiation we receive, this thing that's being measured right now, right, comes from nature. Okay, the Earth, the stars, and other novae, which are star explosions. So I don't know if you know this. All of the atoms inside of you come from exploding stars. Okay, so when stars get old, if they're big enough, they explode. Okay, atoms had to be built. Right? And the only place that atoms are built are inside of stars. Stars undergo a process for what's called nuclear fusion. For example, our sun takes hydrogen and fuses 2 hydrogen atoms together to make helium. Okay? That process releases energy. Okay, and that's why our sun is releasing energy to us. It's fusing hydrogen to helium. Well, when stars get old and die, they, if they're large enough or the right size, they blow up and they spread those atoms throughout the universe. New stars get created, fuse elements into heavier elements, and so on. And all of the elements that you're made of had to have come from prior generations of stars building those elements and then exploding and spreading those elements throughout the whole universe. The stars and novae spread radiation throughout the universe. The sun emits radiation, right? The sun, if we didn't have our protective atmosphere, right, the sun would cook all of us, right? It would not be very constructive to life on Earth. Minerals in our buildings, our own body. I told you a number of something like 5,000 times per second. There's a decay event like that. We can't measure it because it's being absorbed by like the other parts of your body, but on average, that should be the content of our bodies. Smoke detectors, glossy magazines, camping lantern mantles, cigarettes, bananas, drinking water all have radiation in them. You should go to your city's, the mutual water company for your city, and look up their water reports. You can look up in the water reports, there's radiation in drinking water. It's there. It's in low enough amounts. It should be in low enough amounts to where they don't have to like make a big deal about it, but it's in the reports. You can look at the levels of different amounts, different types of radiation in your water. The biggest one here that we have to worry about is radon. Radon's a gas that's radioactive. It comes from the radioactive decay of uranium in soil, and radon gas has the problem where it comes from the soil, and in places everywhere, but in places with poor ventilation, radon gas tends to accumulate, and so you'll see people doing things like performing radon measurements, where you get these little radon detection kits and you put them all over the place, and you can measure the levels of radon in your buildings, for example. Radon gas is accounting for the majority of all natural radiation exposure. And it's in higher quantities near places where there's large rock formations. So near mountains, there's larger amounts of radon. And it comes from the idea that there is higher quantities of other radioactive materials that decay and become radon. Let's talk about how radiation has negatively affected people. For example, in World War II, to end World War II, the U.S. effectively deployed 2 nuclear fission bombs on Hiroshima and Nagasaki that killed hundreds of thousands of people. Right, and effectively ended the war because it was just such a big incident. That's a real disaster. Still having effects to this day. Chernobyl power plant melting down in the Ukraine in Pripyat in 1986. Okay, that was a big deal. That emitted something to the effect of 50 million curies of radioactivity. You don't need to know what a curie is right now. Okay, but it's a measure of an amount of radiation. All you need to know right now is to compare it to an imagined disaster, a disaster that wasn't an actual disaster, but is said to have been. I'm not old enough to know, obviously been around for that, and most of us are not, I don't think. But 1975, there was something called the 3 Mile Island power plant incident, where the power plant had a meltdown event, nuclear power plant had a meltdown event, and emitted some radiation into the surrounding area. It was made of a big deal on national television, and lots of nuclear sanctions were put on these power plants to really try to shut them down. And it only emitted 17 curies. So again, you don't need to know what a curie is. It's a measure of radiation. It emitted 17 of them compared to Chernobyl's 50 million of them. Okay, so these are real bad things that happen that are still affecting the world today. For example, Chernobyl, its radiation leakage has spread to the entire world and actually increased the radioactivity of for example, water all over the entire world. There's entire areas of land in the Ukraine that can't be used because of the radiation exposure there. People still live there, by the way, but it's called an exclusion zone. However, there are people that still live there, and it was a real big deal. I mean, they had to literally abandon all of their equipment. They had to leave all of the equipment there because it was all soaked in radiation, soaked in radioactive material. So just a bad thing, that the Chernobyl meltdown. If you want to watch anything and learn about that, there's so many documentaries on it. And there was a docudrama done a couple of years ago called, I think it was actually just called Chernobyl, but anyways, it's really good. It has some really good high-level actors. Stellan Skarsgård is one of the actors in it. Really good stuff. So, and they did a very good job about it. So if you want to learn more about that, there is more about that out there. But those are some times when radiation has become disastrous. Last couple things to say for today. The benefits of the use of radiation far outweigh the risks, okay, in medicine. However, because it can be harmful, and we understand that the effects of radiation accumulate over time, radiation needs to be managed with a healthy respect, and we need to keep our exposures to our patients, as most of you already know this word, ALARA, as low as reasonably achievable. We only know how to do things correctly now because lots of people died before we got to here. Lots of people had really bad times before we got to here, okay? Again, the reason why we have the regulations are because people had, really bad times. So accidents and diseases in early radiation workers brought to light the need for judicious use of things like lead aprons, shielding devices in modern practice, and the incidence of various disease among radiographers is no different than any other profession or the overall population. Said in other ways, modern radiography is safe. Okay, it's a safe profession with the associated risks about the same level as secretaries, clerks, or school teachers. We have no increased risk above the average person, okay, as long as we do things in the safe way, right? Use it with a healthy understanding that we can, misuse it, right? That brings me to the end of today's talk.